Hey class, today we will learn about functional programming and why you should care about it. If you've taken an introductory programming class before, you've probably learned about concepts like variables, conditionals, loops, and functions. The paradigm of programming that I've depicted in these boxes here, and the one you are most likely to be familiar with, is called imperative programming. It's not super important to have a full understanding of imperative programming for this video, but just know that the type of programming that is most often covered in introductory computer science classes is imperative programming. But what if functions were not just an additional feature? What if functions were the main event? That's where functional programming comes in. You want to use a conditional? Bam, function. You want to do something repetitive? Bam, function. You can even have functions on functions on functions on functions. In the most basic terms, we can describe programs as actions being done to things. For example, print might be done to a string hello world, or +1 might be done to a number 5. If we think of programs as actions are done to things, in some programming paradigms, such as imperative or object-oriented, the emphasis is on the thing. In functional programming, the emphasis is on the action. Let's take a look at how this principle plays out in specific functional programming concepts. First up, recursion. Let's compare the two paradigms in an example where I repeatedly add numbers. In imperative programming, we can repeatedly add to a number using loops like this. Here is some Python code I've written to demonstrate this. I set a variable x to have a value 3, and while x is less than 10, I increment x and then print the value out. In functional programming, we don't typically use loops, instead we use recursion. Here's an example written in Racket. I define a function add_10 that takes in a parameter x and returns x if it is at least 10, otherwise it does a recursive call on x plus 1. Then to get the output, we have nested function calls. We call the print function on the result of calling the add_10 function on 3. We can notice that in the imperative example, we emphasize the thing by incrementing the value of a variable. In the functional example, we emphasize the action by combining function calls. One thing you might notice is that the functional version does not initialize or modify any variables. But wait, you might be thinking, what about these x's? Aren't these variables? These are parameters that go in the function definition, so they don't really count. When we get to the code execution, we do not store any data in variables like we did in the imperative implementation. Next, we'll talk about higher order functions, which you may see abbreviated to HOF. The key idea here is that functions can be inputs and outputs. Here's how higher order functions work at a very basic level. A function takes in some number of inputs and some number of outputs. For the function to be considered a higher order function, at least one of the inputs or outputs has to be a function. That's all there is to it. Now, let's take a look at how you might use higher order functions and contrast it with an imperative implementation you might be more familiar with. Let's say I have a list of 3 numbers and I want to add 1 to each of them. Under an imperative paradigm, I might initialize a variable x with a list 1, 2, 3, and use a for loop to iterate over the list, adding 1 to each value. Lastly, I print x, which should yield 2, 3, 4. In the functional approach, I can define a function add1 which takes in one parameter x, and then returns x plus 1. Then I can use a higher order function called map, which takes in a function and a list as inputs, and applies the function to every element of the list. I can then call the print function on the result of map. Again, we have that the imperative implementation emphasizes the thing by initializing and modifying a variable. On the other hand, the functional implementation emphasizes the action. Once again, we don't actually initialize any variables, and everything is computed with function calls. Focusing on the map function call, we see that we are passing in our add1 function as an input to map. As we said, a function that takes in functions as input or output is a higher order function, so this means that map is a higher order function. Higher order functions are a key concept in functional programming. Here are some more examples from the Racket documentation. Notice that each of these functions takes a procedure, which is a synonym for function, as input. That makes them higher order functions. Now that we've shown some examples of functions as inputs, let's do an example of functions as outputs. Previously, I defined a function add1 that can add 1 to my input. But what if I want to be able to easily make functions that can add any number I want? I can define a higher order function makeAdder that takes a number n as input. Then as output, it returns a function that takes in a number and adds n to that number. Using this higher order function, I can easily use it to define a function that adds 5 to any number. Hold on. If functions can be inputs, and they can also be outputs, does that mean that functions are values? Great question, Tim. And the answer is yes. Functional programming is a very vast topic and we've only just scratched the surface. But if there is anything that you can take away from this video, let it be that functions are values. This means that functions can be passed in as arguments, they can be returned, and they can even be stored in lists and other data structures. Switching gears a little bit, I want to talk about this interesting symbol that I see all over the place. Here it is in the logo for Racket, which is the language that I've used in this video for demonstrating functional programming. Here are some more logos for functional programming languages. We see that in each of them, the symbol features quite prominently. This symbol is the lowercase Greek letter lambda, and not only does it show up in programming language logos, it also shows up in the programming languages themselves. Here I have screenshots of documentation from Python and Racket, and they both have lambda as a keyword. How interesting. The reason for this is that functional programming is based on a theory called lambda calculus, invented by Alonzo Church in 1936. We will go much more in depth into lambda calculus much later in this course, but for now, if you're interested, you can watch this video that I made which provides an overview of the most basic concepts. So, why care about functional programming? One thing that we saw in this video is that with functional programming, we can do things that you were already able to do, such as modify every element in a list, but from an entirely new angle. Even though these different programming paradigms can accomplish the same things, some problems may lend themselves more to certain programming paradigms than others. By understanding functional programming, you'll have another tool in your tool belt that you can consider anytime you come across a programming challenge. Practically speaking, many programming languages are functional programming languages, so understanding functional programming will help you learn these languages. Even if you don't program in these programming languages, many of the more mainstream languages are multi-paradigm, so they have functional programming features as well. As we just saw, Python, even though it can be used for imperative and object-oriented programming, also has lambda functions, which are a functional programming feature. One major real-world application of functional programming is the JavaScript framework React. Many web applications use React, which uses a functional programming paradigm. Speaking of React, as of 2025, which is when I am recording this video, it's a common enough framework that knowledge of React is sometimes required for your job. That's right. Some software jobs use functional programming languages, and again, even if you don't use a functional programming language, you probably will end up seeing some functional programming concepts anyways. So, knowledge of functional programming can help you get and keep a software engineering job. Let's summarize what we've learned today. We learned how to contrast imperative programming, which is what you've probably seen if you've taken an introductory programming class, with functional programming, which revolves around functions. The simplest way to understand the difference between the two is that if we think of programs as actions happening to things, then imperative programming places the emphasis on the thing, whereas functional programming emphasizes the action. One concept in imperative programming is loops. While we typically don't use loops in functional programming, we can accomplish the same things using recursion. We also learned about higher order functions, which are just functions that take one or more functions as input or output. All this led us to the conclusion that in functional programming, functions are just like any other value. We also noticed that the Greek letter lambda kept showing up in programming language logos, and that's because functional programming is built on lambda calculus, which we'll cover later in the course. Lastly, we learned that we should care about functional programming because it gives us a new way of looking at code. It's a paradigm used in many programming languages, even those that aren't purely functional, and knowing about functional programming can help you in any software development job. Thank you so much for watching. If you haven't already, you should check out my previous video on object-oriented programming to learn about a different programming paradigm. And stay tuned for an upcoming video about logic programming. As always, this is your CS Professor of Fun.